I'm Ida, and I am the Secretary of IEEE Women in Engineering. And I'm going to give you a little introduction about what IEEE is, what do we do, and what our main goals are. Okay, so IEEE is the world's largest professional organization dedicated to advancing technology for the benefit of humanity. IEEE Women in Engineering is a global network of IEEE members dedicated to promoting and inspiring women around the world to follow their academic interest in a career in engineering and science. We are one of the world's leaders in changing the face of engineering. Our global network connects nearly 20,000 members in over 100 countries to advance women in technology at all points in their lives and career. At our organization, our main vision and mission is to be able to facilitate the recruitment and the retention of women in technical disciplines globally. We want to be able to build a community of IEEE women and men using their diverse talents to innovate for the benefit of humanity. We want to address ways to improve the climate for women in workplace. Over the past couple of years, we've been able to prepare workshops.
We should do open Zoom meetings, but I think you're going to have to just turn it off because it's started now.
Seminars, both in person and online in different fields, such as AI, innovation, psychology, electronics, and business. If you have any more questions about IEEE Women in Engineering, feel free to email me at ida@bbartech.ca. Without further ado, I would like to introduce our speaker and instructor, Prof. Jeff Edmonds. Jeff Edmonds has been a computer science professor at York University since 1995, after getting his bachelor's at Waterloo and his PhD at University of Toronto. His background is theoretical computer science, and his passion is explaining fairly hard mathematics to novices. He has never done anything practical in machine learning, but he's eager to help you understand the musings about the topic. So thank you for being here, Prof. Jeff Edmonds. The floor is yours. I'm going to stop sharing my screen.
Excellent. All right, we got my screen here.
Yep.
So let me start by saying how excited I am to be here with you all, and thank you for coming. And I've been a little nervous because I didn't really know who the audience was going to be, but when I flip through the faces I recognize, they're all friends, which tell me I'm doing okay. It's going to be quite an introductory. So if you're an expert at machine learning, you might get bored, but I'm hoping to present it in a way where anybody can understand it. And if you don't understand what I'm currently saying on the particular slide, then definitely stop me and ask questions. But if you have something, a broader question, then let's leave it to the end. So let's start by kind of comparing coding and neural nets. So you probably all know about coding. Each line of code was painstakingly written by some coder, and it works really well for simple tasks. You have to tell the computer exactly what you want it to do, and that's what it will do. So in contrast, a neural net, what it does is based on the weights on each of the edges. Each edge has a real number, and these weights are far too hard to understand. Just like the brain's too hard to understand, you'll never understand what these weights are doing. And so where do they come from? They come from a really simple learning algorithm that looks for patterns, correlations in the data, and learns the weights using that pattern. So in the 80s, the machine learning, the expert systems world wanted to be able to get robots to walk and things, and it completely failed. And the reason it failed is that though we all know how to walk ourselves, it's hard to explain to somebody else who's never walked before, like a robot, how to do that. While in contrast, walking has enough of a pattern to it that the machine learning algorithm can find that pattern and learn how to do it. Let me first say that I find this whole process quite magical. It sort of reminds me of or even it explains to me how we evolved ourselves, if you believe in evolution. Because if you have some sort of system and it has this random change happens, and that random change is encouraged with feedback to go in the right direction, then what can emerge can be quite awe-inspiring. And so similarly, with machine learning, we give it a little feedback from our supervisor, our training data, and we get complexity that is quite surprising. And as I say, I find that all kind of oddly spiritual. So
Sorry, Jeff.
Yep.
I have to interrupt you. There are a couple of people that they cannot join because you are the host and you are the only person who can let them in.
Right.
Sorry for that.
All right, let's admit all. Can we say always admit all?
Yeah, you can, please.
Admit
Thank
all. Waiting room. I don't know how to, I've never had a waiting room. So if somebody could keep monitoring that, and I would welcome to the people who just arrived. We are talking about machine learning, I guess you know. And we all know the amazing applications that hopefully will change the world in positive ways. And
protect against vision loss.
And then we also, this one I had to stick in because Toronto is just starting a shuttle program, which is going to be a self-driving shuttle program to pick people up at the train station and take them home. So I'm excited about that. And then we also know about all these scary applications that hopefully won't make the world a worse place. And we will talk more about all these applications on the 7th. You know, we have 7 talks. So on the 7th one is going to be about ethics, and we'll talk about these applications then. All right, so to begin with sort of the mathematics of it, let's have an overview of how it all works. And I really do believe that everything I say today, everybody here should be able to completely understand. So if, as I said, if there's something about the page we're talking about you're not getting, then holler. So here's our robot, and the goal of the robot is to learn to identify faces and bicycles. So this might be what the architecture of his brain looks like. And what happens is, what our goal is an image will come in and it will say face. An image will come in, it will say bicycle, right? And to help the robot, the machine learn, we'll have a supervisor. And she has just tens of thousands of training data. And each training item will have an input, which in this case is an image, and the appropriate label, which in this case is saying face or bicycle. And she's going to help the machine learn. And I've sort of indicated, or maybe already, that what controls the machine are these weights. So just think about them as knobs on the machine that set some real value parameter. And you can turn these knobs to get the machine to do what you want. And we're going to start with, we don't know how to set these values at all ourselves. So we're going to start with completely random values, and we will slowly change them. So at some point in time, we're going to have our current, here we are at some point in time, and we have current values. So what are we going to do with these current values is, well, before we do anything with them, let's let's try to visualize them somehow. And we can think about this vector of real values, putting the machine in some location in the weight space, right? Here's a space of all possible weight settings, and our machine is sitting at one of them. Now, in this image, we only have 2 weights, and they give the longitude and latitude of where our machine is sitting. But you know, really, there are thousands of weights, and so this is a 1,000-dimensional space. But let's not think about that, because that'll scare us. All right, and so the location of the machine then specifies the weights, which in turn specifies exactly what this machine does. All right, so let's take our current settings, and we're going to feed through it all of the thousands and thousands of training data items, right? So the first image comes in, and it says it's a bicycle, and the second image comes in, and it says it's a face, and of course it didn't do that well, but you know, we did give it random weights, so you don't expect it to do that well. And we're going to give all those answers over to the supervisor, and she's going to evaluate how well the machine does when it has these weights. And she's going to compare the correct answers to the answers that the machine gave, and accumulate all that information into one number, which will be called the error. And we're going to visualize that by where the machine is standing, right? He's standing somewhere specified by the weights, and where he's standing, we're going to put a height, which indicates how well the machine did with those weights, right? That's the error. All right, and now the machine needs to learn. And the way it's going to learn is just to make small changes to each of the weights. And it's going to get the supervisor to help it again. The supervisor is going to tell it which of the weights seem to help give right answers and which of the weights seem to be influencing the wrong answers. And as such, the machine will make just little teeny changes in each weight. And then it's standing, because it's made those changes, it's standing somewhere at a different location. That different location specifies different weights of our machine so that it will now do different things. So we repeat what we just said. We feed all the thousands of training data through, and for each image, for each input, it gives some output, and we give all those outputs to the supervisor, who compares the correct answer to the answer given by the machine. And again, she evaluates that with some weight. And you see the weight is a little shorter. This pole here is a little shorter. Why? Because the error is a little better, because the machine learned and is doing a little better now. All right, so that's the whole process. All right, and now I'm going to tell you something that we can't do computationally because it's too big of a task, but it's more of a thought experiment. Suppose that we did the same process for absolutely every place that the machine could learn, right? Every place we set that specified the weights on the machine. We put all the data through the machine. It gave answers, and for each of those locations, the supervisor says what the error function, you know, how much error there is. And if we do that for every location, then that defines some error surface. And you can see the red locations are on top of a hill. So there the error is really high, and we don't like those spots. And down here in the valley, the error is really small. And those are the places where the weights are such that we get lots of right answers. And our goal is to find the low place in the space. And how are we going to do that? It's an algorithm called steepest descent. So when my son Josh was little, we were climbing a hill, And I said to him, Josh, how do you find the top of the hill? And he says, you just keep going up. And I said, how do you know when you get to the top of the hill? And he says, you can't go up anymore. And so that is our entire algorithm, right? We're going to start at a random place, and we're going to keep going down in this direction of the steepest direction until we get to a valley where we can't go down anymore. And then we will hope that the error is sufficiently small that we get the correct answers. All right, does that make sense? Now, just to make, you might be saying, hey, why don't you just stand at the top of the hill and look around and find the valley? But the problem is you're completely blindfolded. So we don't only have 2 weights, we have thousands and thousands of weights. So this is a 1,000-dimensional space. And for any particular, any calculation you want to do is going to take huge amount of computation. So you can't just say, look around, all right? All right, so that is my complete summary of the entire topic, all right? And before we go on, let me tell you something about abstract thinking. So in this talk, as we often do in mathematics, we're going to say very few specifics, right? We don't need to talk about the nature of the machine that we're building. We don't need to talk about the nature of the input X or the output Y, right? We did give specific examples of this might be a neural net and X might be an image and Y might be a labeling cat or dog, but those are just examples. We don't need to be giving you any information about those, right? And if we were looking at images and trying to recognize them as a face, then we will never mention noses, right? So the first time I ever gave this very talk, some students said, yeah, but what about their nose? And so I'm trying to, I added this slide here to let you know we're never going to talk about noses, all right?
Now, Jeff, I'm sorry to interrupt. We still have some people waiting?
Right, I got an emit button here.
Yes, I'm so sorry to do this. Do you want to give me the host? Do you want to transfer it so I don't bother about you with this later on?
Oh, that would require me figuring out how to do that. It's all right. You just holler periodically and I'll welcome the new people. I got a button right here. I can just press.
Thank you so much, Jeff. Sorry.
All is well. So welcome, people. We just finished the intro and we're talking about not talking about noses. All right. So why do we not talk about all of this stuff? And the reason is it helps us focus in on the parts that are important. We simplify and say, what do we need to talk about on this slide? Because we can't talk about everything all at once. And the second reason we do this is because if we don't tell you the nature of a machine or the nature of the problem, then everything we say will work equally well, no matter what model of computation you're using, no matter what the computational problem is, no matter what your input and your output is, it will work no matter what. All right, and so my recommendation when you're listening to me is not to think about, oh, what should Jeff be saying? He should be talking about noses now. Instead, trust me that I'm going to say in each slide something that's the next thing you should learn, and try to focus on what I'm trying to say on that slide. And if you don't understand what I'm currently saying on the slide, then certainly unmute yourself and holler. I probably won't notice the chat. Maybe somebody else will notice it. But if you have something, question off topic, then we'll talk about it at the end. All right, so now let's go back to, right, we're gonna keep going through these same ideas over and over again. And what we're gonna do now is we're gonna just list the topics that we talked about already. So we'll have a sense of what the key topics are. And if you don't quite feel you understand that topic, don't worry, we're going to cycle through them again in more detail. All right, so the first issue is that we're assuming that out there in the universe somewhere is a function that we're trying to learn, right? So it takes some input X, and then the yellow curve will tell you the corresponding output Y, and that's what we're trying to learn. And in order to learn it, we're going to have a huge database of training data. And each of those training data items is going to be one of these points. And you'll see it has some X value, which is its input, which might be the image. And it has some Y value, which we're assuming is provided by the supervisor. And it might be plotted here, or it might be, a label face or bicycle. And so that's our training data. Then the next topic we're going to talk about is machines. And the machine of interest these days is these deep neural nets. So we'll talk about them. But really all you need to know about them is you give them some X value as input, and they give you some Y value as output. So here, see this green curve here, that is representing what the machine will do. You give it some X value, it gives you some Y value. And of course, the goal of the machine is to approximate the answers given by the supervisor as best as possible, right? So here you can see the green curve is trying to fit the purple training data, right? Now, the only other thing you need to know about these machines is that what it does, I mean, you will specify some architecture like this, and then what it does will depend on all of these knobs that you tweak to get it, all these weights. All right. Now, once we have a machine, we can talk about the accuracy of that machine. And the most obvious way is to ask, what fraction of your data set is it giving the right answer, right? If the answer is, if it's a bicycle and it says face, then that's no good, right? But we're going to see that that's not a useful measure for learning. We're going to have a more smooth definition of error, and it's just given the current weights. This is a function of weights. How well does our machine do given these weights? It's you sum. This symbol is sum. You sum over all the training data of how well it's doing on the training data, right? And then given an error function, then we have our training data, we have our machine, we have our error function. And then what is machine learning? Machine learning is just this line here. It says, give me the weights that minimizes the error. That's as simple as that, right? Which weights is going to minimize this error? And that's what we're trying to learn, right? Does that make sense? And in general, this is a very hard thing. You can't just say, magically give them to me. This is some huge optimization problem, right? We're trying to minimize something. And we're going to do that using gradient descent, which is a standard optimization. Newton did this kind of thing. All right. Now, once we have our machine, right, we build our optimal machine. It does really well on the training data. That's great. And then Google says, it's time to drive our car out of the Google parking lot, and let's hope it doesn't kill anybody, right? So the question is, when it's driving out in the world, it's going to see data that it's never seen before, right? So, here's a piece of data that we've never seen before, and we don't have the supervisor's answer for it, and we want to know how well does the machine do, and that's just a big question mark, right? So those were our topics, all right? And what we're going to do now is we're going to go through those topics again. one at a time and expand and tell you more about them. All right. So the first topic was our training data. And here in this graph, you might have noticed that we are kind of pretending that X is one real number along the horizontal and Y is one real number along the vertical, but we're just pretending that so that we can get a nice picture. So as such, each of our training data is one of these dots, right? It has for each X, right? We have lots of these training data, and for a particular one, the Dth one, we have an X value, that's the input, and we have a Y value, that's the supervisor's answer. And but in reality, this X value could be something really complex like an image, in which case it's hard to plot it down here, but you know, let's just work with this picture because it's a pretty picture, right? And so there's our image, and what does the supervisor provide is the Y. Well, if the definition of a regression is that the answer Y is a real number, but in our example, we're doing more categorizing, in which case the answer is a label. Hey, this is a bicycle, this is a face, right? So there's another way of visualizing this training data. In this picture, we are assuming each X value is one real number. Here, I'm assuming it's two real numbers, so I can plot it in two coordinates. But really, you know, each X value has thousands and thousands of values. So this X value is sitting in a very high dimensional space, right? But this picture kind of shows you something. And then what are the colors, right? We will color each point. Maybe the blues specify that it's a cat, and the red specifies that it's a dog, and the yellows are faces, right? And so this is our training data, and our goal is to classify the reds versus the blues, right? Now, just to get a sort of glimpse of what a daunting task this is, right? Our image, here's an image of a cat, right? And you look at it and you say cat, but it's really stored as this huge file of numbers and how can you possibly look at this whole file of real numbers and know that it's a cat, right? We have no idea how a human does it, and we have no idea how a neural net does it, or how we're going to learn it. But that's certainly the task. Somehow by looking at this big file of numbers, we have to learn to recognize that it's a cat. All right, so that's our training data. Everybody getting training data? So let's now talk about our machine, right? So as I told you, a machine is going to take some X value as input. It's going to return some Y value, and what it does is dictated by these weights. What are these weights? They're real value parameters. I'm doing this because I'm thinking it about as being a knob on your machine that you can turn all these dials, right? You have thousands and thousands of dials, and you can turn each of one to get it to do what you want. In general, what are these parameters? Well, anything that the learning process remembers, right? As it's learning and it's looking at your training data and it's remembering something about the training data, will be these parameters. And what do they do with those parameters in the end? They're later going to make predictions on what the answer will be on data it hasn't seen before, right? So any way that any parameters that it sets during the learning process, right, are going to be our weights. All right. Now let's go back to the 80s, or maybe even before. I did it in the 80s, where we're trying to do linear regression, right? We're trying to fit the best line to a bunch of data. And what might this, right? The inputs, each input is a bunch of input numbers, and the output is some real input, real number. And what might they be? Well, the output, well, all our training data might be talking about different days. And then if we're talking about the particular day, little d is a particular day, then the answer for the day will be the likelihood that it rains. And then the input for the day will say, what do we know about that day? Well, we're going to know many features about that day. And the first feature we know about that day might be whether or not there are clouds. And the second feature, oh, I meant to come up here and add a new feature. Let's stick in a feature here. A feature might be whether it's sunny, right? And then a third feature might be what shirt the guy is wearing, right? And then each of these features, right? So each of these features is going to get some real number weight. We're going to weight them, and you'll note that we're going to want a big positive weight on the feature whether they're clouds, because when there are clouds, it's more likely to rain. But when on the parameter, the feature that says how sunny it is, we're going to want a big negative weight, because when it's sunny, it's less likely raining. And similarly, when you have the color of the feature, which says what kind of shirt is the man in the picture wearing, right? Then we're going to want kind of a zero weight, because that doesn't have any influence on whether it's raining or not, right? And so then given these weights, how do we compute? Well, we take each feature and we multiply it by its corresponding weight, and we add up, and that's going to give us our value of whether it's going to rain or not. And how do you learn is, well, we're given everything in purple. That's our training data. And we learn by finding everything in green. Those are our weights. And the green is going to tell us, we find the line that best fits this data, right? And when you do that, maybe you discover something cool, like actually there is a correlation between what shirt the guy's wearing in rain, because if he's wearing a raincoat, then that's how I know it's going to rain, right? So that was a linear predictor. We could be more fancy by making it, let's find the best shaped polynomial or any sort of function you want here. But you'll see what we've added more purple features, right? This value squared and this value squared are just features that some human handpicked. In fact, I had a job as a co-op student in which I was handpicking features like this in order to fit our data. And all those features are computed before we do the learning process. And so the learning process is still just finding weights to balance these features. And so it's still basically linear regression. All right, so now let's look at a more complicated machine. This is a neural net with lots of deep layers. And what does it do? Well, it takes as input an image, and this image has lots and lots of pixels in it. So all of these input values here, each of those red, purple dots will take one input real number, which will tell you the brightness or the color of the corresponding pixel, right? Each of these corresponds to one of these pixels. And then these real numbers go through the neural net, right? So layer after layer of the neural net is going to take these real numbers, process somehow, and then pass them on to the next layer, which will process somehow and pass them on to the next layer. And until the last layer, it can identify whether it's a face or not, right? And let's do that again. Remember, each image was one input value, and we were placing that input value as a dot in the vector space, the space of all images, right? So that's just some dot is representing one image in the space of all images, well, these dots are still different, right? They're kind of telling you the location of this dot in the high dimensional space, right? They're telling you the value of all the pixels. All right, so let's push the button again. And again, it's going to transform this space until it can identify whether it's a face or a dog or not. And if we go back to the beginning again, now I'm showing you all possible images. This is the whole image space, all the possible images. And they have, you know, this one's a face and this one's a cat based on their coloring. And now only one of them goes into the machine at a time, right? So what's being inputted here is just one of these images, but we can imagine in parallel, we can imagine what happens to all of these images as they go one layer down next, right? So all of these images by the first layer gets transformed somehow, and they keep getting transformed somehow until, look at now, somehow the reds and blues and yellows have been separated somewhat, and we can just use kind of linear planes to say which ones are cats and dogs, right? Does that make sense? All right. So let's talk a little bit more about how this neural net works, right? We know that it's all modeled after the brain. And, you know, I don't know much about the brain, but we all know that it contains neurons. And each neuron at each point in time is either firing or it's not firing. And when one neuron fires, it sends a signal along some dendrite and along these edges here, and it either is encouraging the next neuron to fire, or it's encouraging the next neuron not to fire, somewhat based on the weight along that path, right? And then you think about any neuron that's taking in signals. It's taking these signals that say fire, taking signals that say don't fire. And if that signal reaches some threshold, then it's going to fire, right? That's all we need to know about the brain, right? So let's build an artificial neuron, right? This is one neuron. And what's the input to this neuron is this image, right? Because we're trying to recognize whether it's a bike or a face, and we're going to feed it into all of the neurons, right? Well, at least the neurons that are closest to your eye, right? So here's a neuron close to your eye, and we're going to feed in this input. Oops. And what is the input? As you know, it's an image that's made up of lots and lots of pixels. And so we're going to talk about the ith pixel. And so one of these columns, one of these nodes here is about the ith pixel. And we feed the brightness of every pixel into this thing here. Some people like concrete numbers. And so if you think these numbers have any meaning, you're wrong. I just wrote numbers down, right? So I'm going to have all my pixel values between 0 and 1. So these are just saying my first pixel has brightness 0.5 and my second pixel has brightness 0.3. And see how I'm feeding them in. My last pixel has brightness 0.4, right? And so that's how we're inputting the image. It's just all these real values coming in. And then these are all edges saying, how is this pixel going to influence the firing of this neuron? And each of these edges has a real number weight. So let's just write down some real numbers, right? So this, the first pixel is going to influence the firing of this neuron weighted by 4, versus the second one is weighted by -2, right? So the first pixel is going to encourage the neuron to fire, where the second pixel is going to discourage the neuron from firing. And how do we do that? Is we take each incoming number and we multiply it by its corresponding weight. And then we add them all up. All right, so here what we're doing is we're taking this number times this number plus this number times this number plus this number times this number all added up. That's all we're doing, right? We're taking what's called a weighted sum, right? And what about this funny little edge here? You might notice it. It's just so that we can learn a constant that we add in, right? That will help us set the threshold as we add in this constant, right? Does that make sense? And we just do this sum, this weighted sum, and some number comes out. Maybe it's an 18.2, it comes out. And that is going to be our Z value, right? Our neuron is taking all these signals in, there's a weighted sum to give us this, it's its signal, right? And so now it has to decide whether to fire or not, whether this signal has reached the threshold. So let's get ourselves a threshold. That's a threshold. And Y, what's the output Y is going to be Boolean, yes, no, 0, 1, right? Why is that? Well, because in our brain, the neuron either fires or it doesn't fire, right? The picture is either a cat or it's not a cat, right? So we want the Y to be 0, 1. And the way we're going to model this is we're going to feed this Z number through this threshold. And let's sort of study this graph here. If the Z value is some positive number, here's Z along here. If Z is positive, then the output is going to be 1, right? Versus if the Z is some negative value, so here the Z value is over here is negative, then you can see the output is going to be 0, right? It's just basically says Y is 1 if Z is greater than 0, and else Y is 0, right? It's a simple threshold. Now you might say the threshold's all at 0. Remember, but we added that 8 in so we can shift the threshold. All right, does that make sense?
Yeah, so like to mention here, depends on like the values that when you add up. Sometimes when you get, and then also that depends on what functions you're using as well. If your values are too high, then you would have to use another function to make them, to squeeze them more lower. And if the values are too close to 0, then you have to, yeah.
Exactly. All we're learning, what we learn is these green values. And then once we have the green values are fixed, then the machine is just going to take this linear sum. That's going to give me some Z value. And we feed that Z value into this threshold and it fires or it doesn't fire, right? And we call this a linear separator because it's this line, right? We've done a linear operation and we separate out when we say fire yes and when we fire no, right? Now, what can we do with these linear separators? What can we do with these neurons? Well, we can easily build AND gates and OR gates and NOT gates. And then when we have these gates, we can build a computer. So with these neurons, you can definitely build the laptop that's sitting in front of you. All right, that there's no issues about computing power. It can compute anything computable, right? But what we care about here is learning, right? Your laptop sitting in front of you isn't going to learn by itself. And what's the problem with learning is you see this sharp threshold, it's going to make the landscape sharp. And what's wrong with this landscape? Well, here it's really flat, and then you fall off a cliff, and then it's really flat again. And remember, you're blindfolded. So imagine you're walking around in this landscape and you're trying to find a valley blindfolded. How do you find the valley without dying, right? That's just seems too hard. You're going to learn much better. You're going to find that valley much better if the landscape was more gentle, right? So if you were blind on this hill, you would just know which direction was down and you would walk down and you would find the valley, right? So our goal now is to switch from these hard, sharp edges to a graceful edge, right? That's what we're going to do. And why are we doing it? We're doing it so that we can do hill climbing. We want things to be graceful. And the way we do it is we're no longer going to make everything yes, no. We're going to allow there to be some maybe so in the middle. All right. And so the way we do it is we just replace this threshold function with this function, which is called the sigmoid function. All right. And so let's see how the sigmoid function works. Suppose the weighted sum, the real value that we're getting in, is the same really big positive number we got before. Well, before what we got was 1, but now you can see it doesn't give you quite 1, right? It gives you something close to 1. And similarly, if we had some big negative value, before it gave us 0, but now it's going to give us something close to 0. But the new thing is, suppose we're in the middle. Now, instead of falling off the cliff, it's going to be graceful and it's going to give us some value sort of in the middle. All right. So that's this here describes our neuron. All right. And what are we going to do with all of these neurons? We're going to layer them. All right. So that triangle is one neuron and we build them, right? So there's one neuron, there's one neuron, there's one neuron, right? These are all neurons, right? And we layer each neuron is fed by the layer before it and decides whether to, right? Each neuron, this neuron right here, it decides whether to fire based on the incoming values, right? And so, okay, what are we going to do with this? As before, we're going to feed in the image, and as before, right? So we're going to feed in the image here, and we have our weights. And what's the required output to be? Well, the required output is going to be whether it's a cat or a dog or a face. And the way we're going to do that is we're going to have one wire coming out, giving us one real number for each of the possible labels. And each of these numbers is going to be between 0 and 1. And we're going to add this extra condition. The extra condition is that these values are going to add up to 1. And why do we do that? Is so that we can pretend that the machine is telling us that the probability that the input is a bike is 92%. Now, is there a probability distribution here? Absolutely not, right? This 92 is just some number that is returned by our machine, and we're going to interpret it as saying the machine thinks it's most likely a bike. But, you know, it might be a cat, right? All right, so that's what our machine is, right? We know that these input nodes are giving us pixel values, how bright the pixels are. And we know these output values are giving us how much we think it's a dog. But what's this hidden node doing? It's some neuron that's firing as well. And it has no meaning. Maybe, right? Maybe it's saying, hey, does the image have a nose? Right? Maybe it's saying that, but we don't know that, right? It has no meaning designated by a human, right? All the meaning comes from learning these weights. All right. So we have these edge weights, and right, this edge weight here says the influence of the ith pixel on the jth hidden node. And we have all of those weights. So here's a neuron, and all of these pixels are going to influence the firing of that neuron, right? And so how do we do it? Is we take some linear sum, which gives us some z, real value z. We feed that real value z through a sigmoid function, which gives us some 0, 1, some value between 0 and 1, right? And we do that for all of these neurons. And then those values get fed into the next layer, which get fed into the next layer, so forth until we have the answer, right? So that there's no magic here. That's all it's doing, right? And if you trust this to drive your car, then that's what we're doing, right? We're trusting this to drive our car. But of course, you're trusting your brain to drive your car, and that's all your brain's doing too, right? So, and this is all specified by the weights. All right, so that's our machine. That's everything I'm going to tell you about the machine. Let's talk now about the air surface. All right, so let's review where we're at. We have some training data that's coming in. And what did we do with those training data? Well, for every setting of the weights, we can compute, our machine will look at all that training data. And we're going to, given weights, we're going to ask how well does our machine do on each of these training data items. And so here's the particular input. Here's the answer specified by the supervisor. And given our particular weights, we have some machine that's going to output some answer. And here's the answer outputted by the machine. And the most obvious thing to say is, well, did it get the right answer or not, right? And that's sort of a yes, no, hard thing. And remember what our problem with hard things is that you have these cliffs, and it's hard to learn with cliffs. So instead, we're going to make an error function that's smoother. And how are we going to make it smooth? Well, let's pretend for the moment that these aren't labels of cats and dogs, but the output y is some real number. And so the number that the supervisor wants is a real number. The machine is giving some real number. And the obvious thing to do is to subtract, right? And so we subtract those and we get some real number. And we say, okay, great. Then we go, we put that there. And then we come over to the next training data. And we subtract off the two answers, the answers of the supervisor and the answer of the machine again. And we get another number. But note the difference is our second number was negative. Why? Because the machine's error was in the opposite direction, right? In the first one, the machine gave an answer that was too low. In the second one, he gave an answer that was too high, right? And so we have positive and negative errors, and we don't like that. We don't like positive and negative numbers, right? So what we're going to do with all of these numbers is we're going to square them. And why do we square them? A number of reasons. Right here, we just squared each of them. The first reason for squaring them, I alluded to already, is that if you take a positive number and you square it, you get a positive. You take a negative number and you square it, you get a positive. So squaring things makes all the numbers positive, right? Now, we could have used absolute value signs instead. We could have just made the numbers positive, but let's hold off on that. Another advantage of this is that squaring it makes big errors bigger, right? If you take 1 and you square it, you get a 1, all right? But if you take a 10 and square it, right, you get 100. And that's, right, that's getting a bigger error, and maybe you want to do that, right? But you could go back and say, why don't we instead take absolute values? And absolute values, again, have these thresholds where you go from it's positive to negative, and that switches you values quickly, and we don't like these type thresholds. And if we did absolute values, our math would be absolutely impossible. And so instead we square things because everything is smooth and differentiable. All right, so that's what we're doing, is we take the difference for each of our training data. We take the difference, we square the number, and then we add them all up, right? So this symbol here is the sum symbol. It says sum over all our training data. What do we sum up? The value that the supervisor wants minus the value that the machine gave us. We take the difference and we square it. It's called sum squared error. Sum squared error, you may have heard it before. It's certainly that's what I did in the 80s. All right. And this is going to be called our error function. And you'll note it's a function of the weights. Why? Because we're assuming the training data is fixed. We're assuming the architecture is fixed. All that we're playing with is the weights. And if you change the weights, it changes what the machine does, right? So here we're going to plot that. Along here, we'll plot which weights we have. And then up here, we'll plot what our error was, right? For these weights, our error turned out to be 289, right? But let's try some different weights, right? Instead of these weights, let's look at these weights over here. Then, right, we have the same machine, the same data, but we have different weights, right? We have the light green weights and we have the dark green weights. And if you feed all the training data through them, you're going to get different answers. And hence, here's the different answers given by our machine is the dark green answer. And the error is going to be different. If you compute the error, then maybe in this case, we're going to get 400 error. And so we can plot here, these weights has 400 error, while these plots have 200 error. And you say, which weights are better? Well, the one that's better are the ones that has the smaller error, right? And again, we could do the same thing for every setting of the weights, but that would be computationally way too expensive. But as a thought process exercise, we can imagine we do it for every setting of the weights, and we get some weight curve, right? Some weight surface here. And that's, so sorry, not some weight surface, some error surface, right? For each weights, we calculate what the error is, and that gives us this curve, which tells us the error for every setting of the weights, right? And so what's machine learning is we're given the training data, we're given the definition of the machine, and we're given the definition of what our error is. You give, in fact, right now, you give all of those things to Google, and Google will give back to you the weights that minimize the error, right? So in our picture, that there is the minimum error, but we don't care about the minimum error. What we care about are which weights give you the minimum error. And we write that down as argmin. Argmin tells me, give me the weights that give me the minimum error, right? Don't give me the minimum error, give me the weights that give me the minimum error. That's the arg part. All right, does that make sense? All right, so we're back to our neural net here. And in this picture, we're kind of assuming that we only have one weight because we're plotting along this one dimension. But if we had two weights, then we can locate our machine in longitude and latitude, and we have our machine somewhere. And then for each setting of the weights, we had our error. And then we did that for every, here's for that setting of the weights. And then for this setting of the weights, we had a different error. And if we did that for every setting of the weights, we would have an error surface, right? And our goal is to find the optimal values, which are down here in the valley, right? Does that make sense? All right. Now, in reality, we keep having to switch back to reality so we know what's happening. Reality, we have thousands of weights, and so we're blind in this thousand-dimensional space. And just to give you a little bit of a flavor of what we're up against, you might look at this picture over here and say, "Hey, dude, just try all the weights. You want to minimize something over all possible weights, just try them all," right? That's easy. All right, well, let's think about that. Suppose we have 10,000 weights, and each weight has 10 possible values. Then how many settings are there of the weights, right? You have 10 choices for the first weight, 10 choices for the second, 10 for the third. That means you have 10 to the 10,000 ways of setting these weights. And if you don't know, that's a big number, right? So to give you a flavor of how much time it would take to try all of these possibilities, it's put a supercomputer, the best computer ever, on each atom in the universe and have it compute for the age of the universe, and you wouldn't even make the smallest dent in trying all of these, right? So it's just not the way you do things. You don't try them all. All right, so instead, right, we're going to try to do gradient descent And in order to do gradient descent, we need this differentiable function. And what do I mean by a differential function? Well, what I mean is that if I make a small change, an infinitesimal change in one of the weights, right? I move my location infinitesimally, then each of the Z values is just the sum of here's the weight. You make a small change in that weight. It's going to make a small infinitesimal change in that Z value. And then we pass it through the sigmoid function, right? So it's going to make a small change in the output of that, which in the end is going to bubble through and it's going to make a small change in the output of our machine, which then we measure the error. It's going to make a small change in the error. And that's why we have this smooth error function, right? If you take a small step, it only makes a small change in your height. You're not falling off any cliff, right? Does that make sense? All right, so that's all we had to say about error surfaces. And we're flying right along here. Let's talk about what we came here to talk about, which was machine learning. All right, so we started with, in the 80s, learning the best curve, the best polynomial to fit this data, which is just the linear combination of our purple features, right? All the green are just coefficients on our purple features, just multiply, add, and you can. I was going off to a job up at a hospital, and they wanted me to optimize something, and I just did the calculations on the back of an envelope. It's easy to see. Come up with a formula that will give you the optimal weights. All right, and because everything is linear. All right. On the other hand, if you have something non-linear, the joy of nonlinear things is you can compute so much more. But the problem with it is that learning becomes so much harder. All right. And so now what we're going to do it is, as I said, we're going to start with some random value of the weights, and we're going to keep making infinitesimal changes, making it better and better. And we're going to have our supervisor help us tell us which weights to increase and which weights to decrease. All right. And this process is called gradient descent. All right. Oops. So let me first tell you briefly what's happening here, right? If this was our error surface, we're going to start in a random location. And if you started there, you would do gradient descent down to A. But here, if you started here, you go down to B. If you started here, you go down to C, right? So there's no guarantee we're going to get the overall optimal, right? But hopefully you find what this is called the local optimal. And hopefully we find a local optimal that's good enough. Actually, I got this picture from a discussion where maybe actually B is a better solution than C, because even though the air is slightly worse, it's a wider valley. And so you can build more houses down there, right? You can, maybe it will generalize to other data better, but because you have a wider valley. Anyway, that's what our goal is, right? So how are we going to do the learning, right? Well, we need to find the direction of steepest descent. And if you're standing on this hill, I assume you know that this path, and both the path that the walker is taking and the path that the skier is taking, is not the steepest descent. And why? Is because they don't want to tumble down the hill. They want to walk slowly down the hill. So they're taking a slow path. What would the fast path be? Is the direction that the water flowed, right? If you dumped a bunch of water here, it would flow like a tornado down this hill. And that's what we're going to do. All right. So here we have our hill. And as I said, we asked my son how to get to the bottom. And he says, just keep going down, right? And so how do we find our weights to minimize this error? Is we start with random weights. Then here we are with some random location. And then we do lots of computation to compute what our current error is and to compute what direction to head and how steep it is. And based on that, we decide some small step that we're going to take, right? We take some small step, and then we're going to repeat that, right? We know where we are. We calculate the steepest direction. We take some small step, and we keep doing that until we get the bottom of. And when are we at the bottom of the valley? Is when every direction is up, right? When water is pooling down there. If water is pooling down there, then you know you're done, and you just hope that that's a good solution, right? And you stop. All right, and I'm going to call this the optimal weights, but really optimal in quotation marks because they're only locally optimal. All right, and remember again that this is some high dimensional space and computational is expensive, right? So what's really happening is what you know is your current value of your weights. And then you do huge amount of computation to calculate the error on for those weights. And then you do another huge amount of computation to compute your direction. And then you take a little step in that direction, and then you repeat, right? You compute your error, you compute your direction, and you take a step. So how is that done? Well, how do you compute, given their current weights, how do you compute the error? Well, we put those weights on our machine, right? Each weight specifies is the weight of an edge. We feed all the training data through, each training data through here one at a time. The values propagate forward until you get the answer for each training data. Of course, you can do them all in parallel. And then you have all the answers for the machine, the answers the machine's giving. So you can compare those to the answers of the supervisor. You can calculate the error. All right, so that's calculating error feed forward. You might have heard these words. Then we calculate the derivatives. We calculate the slopes by doing feed backwards. We know the errors. So then we ask, how do these numbers influence the errors? How do these numbers influence the errors? And you keep going back and you can say, how does this weight here, if I made a little change on this weight here, how does it influence the error? We want to know for every weight, if you were to change that weight a little bit, does it make the error better or worse, right? All right, we're moving along, running out of time. So now let's talk about our last topic, which is generalizing the data, generalizing from new problems we've never seen before, right? So what's happened? We were in the Google parking lot. We had lots and lots of training data. We used our learning to learn the weights, and that was great. And it's optimized, right? We optimized this function to do as best on the training data as we possibly could. And now, and see here, this input, it's, we're trying to get it so it gets the right answer from all the training data. That was great. And now we're ready to leave the Google parking lot, and we're going to see data that we have never seen before. And it's going to have answers that we've never seen before, and we have no supervisor to tell us the answer. And we want to know, how well would this machine do on this data it's never seen before? And it's a big question mark, right? It's a big question mark. So let's try to understand it by looking at 3 examples. All right, and in all 3 of these examples, we have the exact same training data, and we learned 3 different machines. And so the first question you could ask is, which of these 3 machines does the best on the training data, right? And if you look, oh, this machine does best on the training data. In fact, you can see it gives the perfect answer on the training data, right? But then you could ask, which one do you think is going to give the best answer on data you've never seen before? And I hope that your intuition will be the middle guy, right? And well, one thing is we can prove is this thing called the no free lunch theorem, which means no method that you come up with will always be able to generalize well. But there are some ideas that hopefully principles that we can use. And the principles are underfitting versus overfitting. All right, so what's underfitting? Underfitting is when your machine, you can see this machine here, just doesn't have the capacity to learn our training data. It's just not going to learn the training data, right? And so it's certainly not going to generalize because it can't even learn the training data. That's called underfitting. Overfitting is when you have such a powerful machine, it can absolutely learn the answers for all your training data. And the way it does it is by it just copies down all the answers. It has enough power to write down all your answers. And if you did that on your test, you copy down everything the teacher said, you would probably learn nothing. And when a new question comes on the exam, you would be stuck, right? So how should you study for a course instead? Is you should take all the material taught in the course and you should compress it. You should summarize all the material down to a little piece of paper. And in order to do that summary, hopefully you understood it somehow, right? And then hopefully when you have a new question, you can answer it better because you've summarized the material. In order to summarize the material, you had to understand the patterns in the data, all right? And this somewhat comes from, you probably have all heard of Occam's razor. It was fundamental in advancing science. He said, if you have two models of lightning, one that talks about electricity and one that talks about the gods, then go with the one that explains the data in the simplest possible way. And that was Occam's razor. All right, so we're moving along. I think we can finish these slides. What do we mean by compression, right? I was talking about compressing the information. Well, the complexity of my machine is going to be how many weights do I have, right? If I have more weights, then I'm somehow I have more power, right? And so here we have 100 weights, here we have 1,000 weights, here we maybe have 20,000 weights, right? And how big is our data set? Well, maybe our data set only has 10,000, right? We have 10,000 data set. Well, this machine has 20,000 values that it's learning with, right? Now, these answers, these Y values are somehow, they can be reproduced from the weights. And what do I mean by that? Well, let's suppose that the input, the X values are fixed. Everybody knows the X values, right? And what we're trying to learn is the Y values. Then if we know the X values and we know the weights, you can plug all the images through and that will give us the Y values, right? So from the weights, we can reproduce the Y values, right? So, and that means in some ways, right, these 10,000 numbers, which are our Y values, are encoded into these M weights, right? We've encoded them in, right? Because we can get the Y values back. And how did we do that encoding? How did we do that encoding? Is, well, we had the Y values and we had the input X's and we did machine learning to learn the weights, right? So from the Y values, we learn the weights. That's an encoding process. And how do we decode is, well, you know the weights and you know the X images, you can recover the Y values, right? So that's an encoding and a decoding, right? So that's compression. It's like any compression that you would do. You have some image, you want to shrink it so it can fit on your file better, and you want to recover the image back again. That's compression, right? And we're compressing with fewer values, right? So here, if we compress these 10,000 values into 100 values, we're just not going to be able to recover the 10,000 values, right? And here we're doing some compression, right? We're compressing 1,000 values, 10,000 values into 1,000 values, right? That's a 10-fold. We're making our data smaller, right? While here, there's no compression at all, right? You can certainly remember 10,000 numbers if you can store 20,000 numbers, right? So no compression. All right, so we're running out of time, but let me give you this picture here. It's a really cool picture. The horizontal axis is how complex our machine is. Here we're saying it's complex by how many numbers are used to describe the machine. And our vertical axis, right, is going to measure how many errors does the best machine of this complexity, how many errors does it have? And we have two curves. The first curve is how well does the machine do on the training data, right? And you can see that the more complex your machine is, the better it does in the training data, up to the point where it gets all the right answers on the true training data, right? It just perfectly can memorize the answers on the training data, all right? But what about the other curve? The other curve is how well it does on general inputs. And you'll see down here, we have underfitting. The machine's just not complex enough to learn anything, right? While here, it can memorize the answers for the training data, but it doesn't do well on data it's never seen before because it's never really actually had to learn anything, right? But in the middle here, it had to take those 10,000 numbers and compress them into 1,000 numbers. So it needed to learn some pattern of those 10,000 numbers. And by that, it can then generalize better, right? So our goal is to find this sweet spot, to find the machine that's sitting right here, right? And how do we do it? Well, one way of doing is a thing called regularization, right? So what it does is it tries to find the best weights that not only minimizes the error on the training data, right? That's what we were trying to do before. We were trying to find the weights that minimize the error in the training data, right? But now we're also trying to find the weights that are somehow not too complex. We want this distance to be small and this distance to be small. And we're going to do some trade-off between the two. And hopefully that will find us in the sweet spot where we generalize well. All right. Now, I told you that the measure of the machine was how many weights we have, but that's hard to change as you go. So instead, we're going to have the measure of the machine be the sum of the squares. And you'll see if you have lots of big weights, then the n's big. But if you have lots of weights that are close to 0, then our weight's small. And this also is a differential function. So we can do hill climbing, we can do gradient descent here. All right. And okay, we have 2 more slides. The second last slide gives us a little theory. The theory is, what we're assuming is that the universe has a probability distribution on our input images X, our input images, right? So we randomly choose our input images and we label them with whether it's a cat or dog. And then we find some machine that does well in the training data. And we do it with the machine that didn't memorize the answers, right? It had to do some sort of compression. Then you can formally prove, and we will do that in our third talk, we will prove that with high probability, if you take more data from the same distribution that we took before, then data you've never seen before, then your machine will, with high probability, will do well on that machine, that new data as well. All right. And one last slide, because I know we're all tired, is about singularity. We all know that that technology is growing at an exponential rate, but actually, if you tweak the differential equation slightly, it's no longer grows exponentially, but it reaches infinity at some point in time. And if at 12 o'clock, it's modeled to have an infinite amount of of technology, then what does the world look like after this? And that's the question we're going to leave you with here. Oh, I lied to you. I have more slides. All right. We have 7 talks scheduled, and we just did the first one. And if this amused you, we can go into further talks. The next talk is going to be more for people who don't know mathematics at all. We're going to review algebra. We're going to talk about linear separators. We're going to talk about matrix multiplication. We're going to talk about derivatives. We're going to talk about back propagation. And my fear is this is way too much for one talk. And so maybe we'll stick some on other talks which are shorter. Then, as I told you, the second talk will be how we generalize to data we haven't seen before. And then this one is how do you learn how to make margarita when the reward comes later. And if we have time, we can talk about other types of models. And then here we're going to talk about statistics and how we can take lots of numbers and compress them into fewer numbers. I think these are cool. These are a model where you have some distribution that you're going to learn, right? You watch people. You watch people make art, and now you want to make new art that no one's made before, right? So you learn the distribution of what does art look like. We can learn about clustering, and then our last talk will be more of an open discussion about ethics. And I finished, then there are more things that I could teach you if you want, and that's the end. All right, so we now have exactly 5 minutes for questions. Should we open the floor to anybody who wants to talk?
Thanks a lot, Jeff. I'm just keeping an eye on the chat box. I don't see any questions, so please feel free to unmute yourself, ask any question, or just write it down on the chat box. So, and I can help with reading that over.
I have a question there. My name is Brandine. I'm a professor at Humber College. I really, really enjoyed this talk. I built a neural network in 1996, and I wish I would have had your talk back then to give me the basics. Instead, I was reading, Simon Haken's book and figuring out myself. And I built something that I trained on a 486, and it took days, and there it was. But the one question that I had that came out of that, when I was talking about it with people, and I haven't delved into that area since, if you're training something, say, can you see tanks in this photo, right? Can you find tanks in this photo? And you, like you said, you don't really know what it's doing. So you think you're training it for tanks,
right?
But what if you're really training it for like trees on the left and, something dark in the other corner? You know what I mean?
Right.
Like, and these are, I like things to be very black and white. So even though I love the magicalness of these, there's a part of me that is always like, but, right?
Exactly. And I can't say anything answering you except exactly.
Well, I'm just glad that I'm not the only one that
no,
is,
no,
wondering,
that's the
right?
classic. Is what are we learning here, right? And that's where you go out into the world and you suddenly realize, no, I didn't learn. All I learned was the color of whether it was sitting on grass or whether it was sitting on pavement, right?
Yeah.
And that's the whole ethics question, right? What are we learning about Black people? What are we learning about anything?
Yeah.
And one thing I want to point out from what the person said is there's nothing here that I said that I didn't learn as a graduate student in the 80s, right? There's just no new math. All that we have different is more data and faster computers.
And I'm glad we have faster computers.
Right. Thank you. Yeah, thanks for your question. That was great. I'm glad you enjoyed the talk. Any other thoughts?
Hi, Professor.
Hi.
It is a fabulous session. I thoroughly enjoyed your class today.
Excellent. Hey, I just saw a picture of Armel. Armel and I worked together in Africa. Any other thoughts?
Hi, Professor. I really enjoyed your presentation, every part of it. I'm now intrigued, like I wrote in the chat, I'm intrigued to know more about machine learning now, and I'm eager to learn more. Much as I would like to do that, I didn't really understand a lot of the things you said, but yeah, I would love to learn more.
Excellent.
I'm just a novice at this, so.
Excellent. Well, let me add something other. I do think this is something everybody can learn. And I do think that if we have jobs in the future, they will be in this field, right? That and social sciences of how to be nice to each other. But if you're hoping to get a job coding, they probably won't be, you know, this is the future of coding.
Yeah, I would love to see what you're going to say in the next session.
Excellent.
Yeah. Thank you.
Thank you.
Hey, Jeff, there's a question in the chat there, and it's just sort of disappearing in the scroll. So it's saying that someone is very interested in theoretical machine learning now, mainly the proofs. Any way to help, Jeff? And are you doing research in that direction?
Me, I'm hoping to do research. I grabbed last year, I grabbed a student who wanted to do machine learning, and we did a paper on fairness, and it just got accepted into a conference. So that's, now I have one paper in a machine learning conference. And if people want to work on things together, let's do it. I'm in my second year class, we're going to get people to try to do some machine learning. And I'm teaching a course next term in Africa in machine learning. But York won't let me teach machine learning because they need me to teach algorithms. But
Thanks.
certainly thousands of papers get written every year on this topic.
I don't see any other questions on the chat. Obviously, there are a lot of comments about how good this presentation was. So,
all right, excellent, excellent. Thanks so much. And let me say something. Can you still see my screen? On the bottom there is, oops, bottom somewhere. I lost it. Let me put in the chat. I think I still have it. There is, I made a web page that listed all the topics for the 7 things, and I will hopefully get the videos from this, and I will link them in there too, so you can look at that link and see what's happening.
thank you, Jeff.
Right.
I do see there are a couple of questions about the recorded sessions, if that's going to be shared, and how you're going to find the link for the next class. Mariam, Ida, are you here to answer that question?
Yeah, so all the classes are already posted on IEEE vTools. I can share that link in the chat so that everyone can have access to it. You can register through vTools, and from there I'll be able to share the Zoom link in the morning, like maybe a day before or in the morning of the class because of security. So I'll share the link in the chat box right now.
And where will the videos go?
The videos, they can be uploaded to YouTube. It's up to you if you give permission. We have an IEEE YouTube page that we usually upload the seminars and the sessions there. I can also share the link after it's uploaded.
Excellent, excellent. That would be great. And if you give me the link, then I will put the link on that my own personal webpage so people can find it there too.
Yeah, for sure. That would work. Thank you.
Armel's question, I don't know if anybody's going to be emailing anybody. So these talks are happening this time every week for the next 6 weeks. And you can email me or go to my webpage and find, I'll try to put a post. Anything I know, I'll put there. All right. Are we done?
I think so.
All right.
Thank
Well,
you so
thanks to
much.
everybody.
Jeff,
Thank you.
could you please just wait a couple of minutes whenever actually, yes, sorry for that.
Oh, no,
So
no,
thank
no,
you,
no.
everyone. Yeah, thank you, everyone, for
Thank you.
Thanks everyone
really
for joining
appreciate
today.
it. Thank you. Thank you so
Thank
much.
you,
Great.
everyone. Thanks,
See you
Jeff.
guys next week.
It was great. Thanks.
Thank you.
Okay, thank you.
Bye-bye.
We
Everybody.
just want actually to
Bye-bye.
make sure. Jeff, sorry for bothering. We want actually to make sure that everything is aligned with the being a host or co-host. Sorry for that.
Oh, no
So-
problem.
Maybe for the next few weeks, I can take on the we'll see if, I think in the Zoom, you can actually have a co-host, but it needs to be scheduled, like the meeting needs to be scheduled like that. So maybe from next time, we'll make sure it happens. So you don't have to do that. But thank you so much,
No
Jeff.
problem.
So I tried to do that. Apparently, it depends on the type of Zoom account that you have. It only allows me to choose one host for the whole event. But I'll follow up to see if there's any way that I can make a co-host for the
Yeah,
next.
And I think
that's true.
probably the only main issue is once we've started, is there a way to just say people can come in, get rid of the waiting room?
Yeah, but we never know if something happen, it would be better that someone else has also have the control. So
Right.
to mute someone, or for
Right.
example, so
Right.
today it happened a couple of times. I decided to mute someone, but
Right.
I have no power. So
Right,
thank
right.
you. It was a great presentation. I really enjoyed the session, and just whenever actually we are closing everything, Jeff, it may happen that you get the record. I'm not sure, because you were the host, final
Oh, all
host.
right.
It may happen that it comes to you.
As an
Again?
email, maybe?
No, it comes and sits on your machine. So accept it if it happens.
All right.
Just-
Well, I turned on the recording and I pushed record to cloud.
Okay, that's okay. So we would see that.
So
Okay.
it shouldn't come to me. It should come to
the
somewhere
host.
that you have
Yeah.
access to.
Okay, thank you. That would be awesome. So Ida, can you follow up with Dustin?
Yeah, for sure.
Okay, thank you. I really appreciate everyone. Thank you, Nadia. Thank you,
Yeah,
Ida.
It was
And
lots of fun.
Thank you.
And
thank
again,
you,
guys, if
everyone.
next time we can't figure out the co-host part, I'll volunteer my hand to host. So Jeff, you don't have to worry about that next time.
Excellent. Thanks so much. And
Yeah.
if anybody gets any sense of the next talk is doing algebra. So again, I need to know what level to put it at, right? Am I talking to, Jake was here. Am I leaning it to Jake, or am I leaning it to that professor who was talking, right? It's a very different algebra talk.
Yeah, maybe it's up to you.
All
You're
right.
an expert. Yeah.
All right.
Make it easier.
Excellent.
Thank you. I appreciate it. Have a nice actually evening.
All
Take
right.
care,
Thanks
everyone.
so much, everybody.
Thank you, everyone.
Love
Have a
you.
great
Take
evening.
care.
Thanks,
Bye.
everybody. Take care.
Bye.
Bye.
Goodbye.
Bye.